Yeah, good morning, it's Charlie ZL2CTM. Well, I just want to follow on from yesterday's experiments with the BD139 push-pull amplifier. And so I got up this morning and just reviewed that table of results. And it was pretty clear that the best performance out of the amplifier was with a input transformer, or T1, with a turns ratio of 2 to 1. And then the output transformer with a turns ratio of 5 to 5, or in other words, n equals 1. So if we look at the input then, so n is 2. So 50 divided by 2 squared, or 4, gives us 12.5 ohms base to base, or in other words, 6.25 ohms per side. So that's I guess intuitive. It's certainly a lot lower than initially with the RN calculations, but this is certainly more in line with what I was thinking in the first place. In regards to T2, so n equals 1, so 50 divided by 1 squared is 1, is 50 ohms, so that's collector to collector, in other words 25 ohms per side. So if we were then to sort of take that 25 ohms and punch it back into our formula for RL, so RL equals VCC squared minus V sat, that's all squared, sorry, divided by 2 times power out. So if we were to rearrange that formula and make power out the subject, we can then feed in our two values of load resistance. So in the first case we'll use 25 ohms, and then in the second case just divide that by 2 just for interest's sake. So again, so we plug it into here, that gives 3.5 watts per side. So that gives 7 watts total, which is pretty well smack on in line with what we actually saw out of the amplifier. Conversely, if we were to right or wrong think, well, we have two devices in parallel, maybe we should divide that by 2, then that would give us same formula, but this time now 12.5 ohms would come out at 7 watts per side. Well, clearly the amplifier is not generating 14 watts, so this would appear to be the correct approach for calculating RL for two parallel devices on each side. So I guess that's in the absence of anything else definitive, and I haven't found anything definitive in the textbooks that I have here in regards to parallel devices, this seems to be the approach. And I guess that sort of makes sense. Either side, those two parallel devices are seeing 25 ohms, and therefore the current through those devices are then shared as a function of 25 ohms. So I guess that does make sense. Right, so what I want to do now, I'm going to break this video up into 6 little experiments. What I wanted to do was first run the amplifier with our most efficient, well, not most necessarily efficient, but certainly the best configuration. So 2 to 1 on the input and a 5 to 5 on the output. And what I want to do is I want to play around with 3 different types of output transformer. The first one is going to be what's currently in the radio, so again in the amplifier. That is a T50-43. And just want to run the amplifier flat out just to see if that's starting to saturate or not. I'm then going to substitute in a binocular core here, so that's a BN43-202. Again, that's currently set up for 5 turns to 5 turns, so all things being equal. And then finish off with a much larger binocular core there, the BN43-3312. Both of these came from kits and parts. So that's what I want to do. So I want to do 3 initial experiments just to see about saturation at the that sort of 7 watt level. I then want to continue on, and in a couple of the texts and various pictures I've seen around the place, had a few examples of where there was a 10 ohm and in some cases a 15 ohm resistor from in a push-pull arrangement from the base to earth on each side. So I just want to do that and to see if that has any impact. I then want to switch to, I might just switch these two around actually, it doesn't really matter. I then want to bypass the emitter resistors. I've got a ton of these, so I'm going to use in this particular case 10 nanofarad capacitors just to bypass the emitter resistors. Hopefully I can get the soldering iron under there and do that, just to see what impact that may have on the gain. My expectations is, from an AC point of view, it should increase the gain. From a DC biasing point of view, it won't have any impact. And then finish off by reverting to diode biasing, just to demonstrate that you don't need to have an elaborate biasing arrangement here with the tip 41. You can get away with just a simple 1N4001 and a reasonably butty, as we would say, resistor from VCC feeding that, which we'll have a look at the very end. So I'm just going to break here and set things up, and like I say, first things first, we'll run the T50-43 flat out, have a look at the scope picture, and then, like I say, swap to the other two cores and see how they work out. So back soon. Okay, so right, let's key the amplifiers. The amplifier's now keyed. We've got 7.1 megahertz going in. That's at our 10 volts, and then that's now as much as I can possibly squeeze into it. The time base is as high as I can go. Let me just crank up the intensity a bit there. I can't do much better than that, I'm afraid. Sorry about the shadows. Can't really do too much about that. Yeah, so there you go. If we were to come back down, out of focus there. So that's now down at sort of that 7 volts peak to peak, and as we go above that, so 8, 9, we're starting to get a bit of distortion there, coming in a little bit more distortion. That's at 12 volts and then all the way through to 20 volts. So I don't know if those peaks there is a little bit of saturation coming through on the highest peaks, or there's some other non-linearities coming through with the actual devices themselves. We're still running on quite a bit of, we don't have any crossover distortion there, but we're still sitting on a reasonable amount of biasing current there. So anyway, so what I'll do is I'll drop that back down to 0 and we'll swap over to the BN43-202 and we'll just see if there's any other difference. Rightio, so we got the second transformer now in place. So we go back to the O-scope, and let's now key up the transmitter, keyed, and we'll increase that amplitude again. So now sitting there at, that's 9 volts, that's 10 volts, then all the way through to 20 volts peak to peak. So very similar at the 20 volts peak to peak range, and if I was to come down, we're still relatively linear. Well, we're linear sort of there, I guess, and then we're starting to get some distortion coming in there through at 7 volts. So I'd argue that is very, very similar, if not the same, as the FT50-43. Right, let's crank that down to 0. We'll just pause there and we'll put on the much larger BN43-3312. Right, so now we've got the much larger transformer on the output. So let's go back around to the O-scope. Let's have that go into focus, and then start cranking that up. So that's now, whoops, let's key the transmitter, that helps. Again, that's 7 volts. So again, we're starting to see exactly what we said before, all the way through to 20. Now, arguably 20 is not quite as pointy, so it does look subtly different. Focus there. But I would argue that that is pretty similar. So I don't think, because I'd expect that there's much larger binocular toroid there would not saturate anywhere near as easily as the smaller ones, being the size, and certainly not, I wouldn't expect and I'm just getting out here, a good 8 watts, or just over 7 watts, sorry, coming out. So I certainly wouldn't expect that. So I think for all intents and purposes for a rig this size, i.e. with 5 watts, we could probably get away with using a small toroid and save this much larger one for a much more powerful transmitter. So I think, you know, for cost, these little smaller binocular cores here are pretty cost effective. So I think I'll go ahead and just use this one. If I was to use this amplifier here, use this one in place of that much larger one and save that for something else. So what I'm going to do now, I'm going to put that back into the circuit, and then I want to move on to attaching those two 10 ohm resistors from each base to earth, and we'll have a look at that. Okay, those two resistors are sitting there. They're currently only connected on one side, so what I'm going to do now, I'm just going to put the camera back onto the oscope. We'll set up for a standard reading coming out, and then I will then tack those two down, and we'll see what impact that has. So let's just move back up to here, sorry for the jerkiness. Right, so those are currently out of circuit. Let's key. We've got that smaller binocular core back in again. So let's go for, that'll do. So that's 6 volts peak to peak coming in. So that's producing, we'll leave it there, shall we? Close enough. I'm going to leave it there. That's just sitting on just under 5 watts. Let me just focus that. So let's now just tack those down. So I'm going to unkey it, tack them down, and we'll key back up again. So just for interest's sake, what have we got here? We've got 1, 2, 3, 4, 4 point, pretty close to 4.7. So we'll go with 4.7. Yeah, 4.7 divisions. So let's just unkey that. I'll keep the camera running so you have to listen to my dialogue. So we'll solder that one down, and then we'll solder that one down. Right, so those are now both in place. Let's key up again, and straight away I can see a reduction there. So that's now down to 1, 2, 3, 3.5 divisions, and we'll drop back down to about 2 watts. So nothing spectacular there. I think from the textbooks it was more around stability of the amplifier, and at this stage of the game I haven't seen any indications of instability with this particular amplifier, so I'm going to pull those back out again, and unless I can be convinced otherwise, I don't see any need to have those in. So those have now been removed, and there we are back up to that original power level. Right, so the next thing I want to do now is I want to take away that biasing network there. So let me just unkey that, and I'm going to replace it with a 1N4001. So they'll go just here. We'll have a little 1 microfarad capacitor sitting across that. We'll remove this here, and in its place here will be a resistor that will then define how much current passes through this diode, and then also by converse of being in parallel, how much current then passes through the two sides of our push-pull amplifier. So what I'll be doing is I will just measure how much current is going through in the current configuration, and then I'll find a suitable resistor to generate the same current, and then just show you that indeed you get the same power out. It's which would expect. Yeah, I've just actually noticed that according to my notes I was going to do the bypass of the 2 resistors. I'm actually just going to, I've just been talking about doing that, so we'll do the biasing first and then we'll bypass these, and we'll see what impact that has. So back soon. Okay, so I've now got that that diode in place there. You can just see it sitting over there in the corner. So that's running from this well, it's not quite VCC because it's been dropped down by this resistor here, but it's running from there to ground. Sitting across it is a 100 nanofarad capacitor and a 1 microfarad capacitor. And then over here we have, in this particular case, it's turned out to be a 100 ohm resistor. So if we were now just to, apologies for the movements there, key that up, there we're seeing there, they'll gradually drop down to bit, again that sort of 420 odd milliamps of quiescent current passing through the two sides of the push-pull amplifier. That's just getting slightly warm. If that was a 1/4 watt resistor, that certainly would be nowhere near enough for the current that's passing through it, the power dissipation. This is a 3 watt resistor, and that's fine. So that's the only downside of using this simple biasing arrangement with the diode. If you go back to the first video, you'll see the schematic with the resistor determining how much current's passing through the diode and then ultimately through the two transistors, or in this case 4. But yeah, it's certainly a simple way of doing it. And again, if we just back over to there and we were to crank up the input again, then we're seeing no difference. So back down to our, in fact in this particular case we got here 10 volts peak to peak, so that is our 1/4 watt going in, and we're getting out there in excess of 5 watts, so we're getting quite a bit more than 5 going out there, which is quite good, more like 6 by the looks of it. Right, so what I want to do now, I'm going to leave this simple biasing network in place, that's fine, and I'm going to now endeavour to bypass those two those emitter resistors there, the big ones down there, the 1 ohm resistors, and we'll see what impact that has. So keeping all things equal, we won't play around with the biasing. We'll leave it on a 1/4 watt coming in, and we'll just measure what we're going to get coming out. So all things being equal, that is 1, 2, 3, 4, 5, 5.1. So 5.1 divisions, and we'll see what happens. Back soon. Okay, those 4 10 nanofarad capacitors now are in place across the 4 emitter resistors. Bit of a pain, but we got them in. Okay, so again, let's spin back around. Let me just close that curtain, might make it a bit easy to see. Alright, so keeping all things equal, back up, so we've got 10 volts coming in, so it's exactly the same as we had before, 10 volts. And then let's now key it up, and we'll see what we get. So, right, so we said we had before 5.1 divisions. 1, 2, 3, 4, 5, 5.3. So a little bit of an increase. If we were now to crank it right up, so what can we say there? 1, 2, 3, 4, 5, 6 divisions. We're indicating about 8 watts coming out. Let me do this, and that one 6 into 10 times squared 50 divide. So 8.9 watts supposedly, if I go from the peak maximum amplitude coming out. Right, so and back up to, like I say, our standard 10 volts peak to peak, or 0.25 watts, or 250 milliwatts going in. And I think we just said there it was 5.3 divisions. So 5.3 10 times for the 10 times probe, run 1 volt peak to peak. Divide that by 2, multiply it by 0.7071, square that, 50 divide, gives us 7 watts. So that there is a 2 watt, let me just double check our figures from before. If we were to just come down here, so these are our figures from yesterday. So that's in focus, yes it is. So we had yesterday, and we've got configured today, a 2 to 1 on the input, 5 to 5 on the output. We had a maximum of 7.5. That's up now about 9 watts. And we had for 250 milliwatts going in for that particular configuration 6 watts. and now we're getting, like I say, 7 watts. And then we just drop that back down to 0, and we're indicating, so we are slightly higher on the bias current, so I would certainly grant you that. What I might do now, just for interest's sake, I'm going to take out that diode biasing. I'll put back in this one, which allows me to have much finer biasing adjustment, and I'll bias that back down to that 400 milliwatts, say again milliamps total current, and we'll just see what difference that makes in terms of the power. Okay, we're back again. So back in place is the variable bias. We are keyed there. We have just sitting on there roughly 40 millivolts, which equates to 400 milliamps passing through the amplifier. And then if we were to go back up to our O-scope and bring that back up to 10 volts going in, and we're still getting out there 1, 2, 3, 4, 5, 5.3. So we're still getting through without there the same these same overall amplification than we had. That's still nice and cool. And when I say cool, they're just warm. I'll have to crank that up to maximum power, so we're getting about 9 watts coming out. Again, each one of these devices should be good for 8 watts. This is not the biggest heatsink in the world, but you know, this is now CW just going flat out, and that's fine. Warm to touch, but you know, like I say, I'm clamping my hands on as hard as I can, and you know, not a problem at all. So yeah, all in all, quite interesting. I'm just going to put back in again that diode biasing, and then we'll do some final comments. Okay, so back again, just put back in again that that 1N4001 diode and its equivalent. In this particular case, it's a 100 ohm resistor there, and as we can see there, we're back up to that same power level as we were before, and up there, well and truly over 5 watts. So 5 watts is that mark there, 10 is here, so we're sitting on about 7 odd watts, which aligns with the maths. Okay, so I'm not entirely sure what else I want to do with this amplifier for now. There was no attempt to make this a broadband, amplifier. So you know, I'm just cranking up now to 14 megs, and I'm still getting out just under 5 watts. 20 megs is now dropping more down to 3, so it was never going to be a massively broadband amplifier, but I think for an amplifier that sits in that sort of 80 meters and 40 meters, I think it's pretty good. So you know, for a quarter watt in, we're getting, what did we just say before, about 7 watts out, I think, sorry, 7 watts, which I think's pretty good. And it just means that the driver that goes into the PA doesn't have to be so large. You know, you're only providing now a quarter of a watt as opposed to say 1 watt. So that's good. Yeah, so I'm not sure, like I say, what else I'd like to do with this. You know, initially I thought that, you know, right or wrong, it might be possible if these things are rated at 8 watts each, at 16 watts per side, run them at half that power, so 8 watts, 8 and 8 is 16, you know, it'd be sort of nice to sort of get around there, but I don't believe that's probably possible with these particular devices, given what they're not designed for high gain HF/VHF use. But in terms of being cheap and cheerful, I think great. And as you can see there, you know, this amplifier has, you know, next to nothing for it, just a little bit of a biasing on it, an input and output transformer, a bifilar wound choke type arrangement there to provide the VCC, and there's probably no reason why that couldn't have been a center tapped primary there to provide the VCC for the collectors, but you know, this is a configuration I've used before and I quite like, and it seems to work well, so I'm going to stick with it. But like I say, to finish off, it's not a bad little amplifier, and I think I might put this on the shelf and use it again at some stage. If there's anything else, sing out. Otherwise, I will leave it there. And what I do want to do next is I want to have a look at a suggestion for a FET antenna amplifier, which I will use in this rig that we built before Christmas, which I don't really want to pull apart, and I certainly want to use as a test bed for playing around there. So let's jump it up there. That particular amplifier there is the antenna amplifier, which comes after the bandpass filter. So I think redesign that, and like I say, use a FET and probably an MPF 102, again in that sort of desire to use readily available parts. That seems like an appropriate one to use. So I might do a little bit of research and a bit of thought and do a bit of experimenting around to see if we can get a nice, again, maybe variable gain, but certainly 10 dB around there would be good, which would be in keeping with what this particular amp is here. So that'll be the next experiment to play around with. Okay, cheers all. Thanks for all the comments, and keep them coming. And happy homebrewing. See you then.